Understanding Interest Rates, Chapter 5, Part 2. Following are the learning outcomes from this presentation. After going through this presentation, students will be able to compute present and future values of multiple cash flows. So far, we've seen how to obtain present value of a single future value cash flow or the future value of a single present value cash flow using a certain given rate and a certain given time. Or we've seen how to obtain one of these four factors of the time value of money equation using the other three factors, assuming that the intermediate payments that were there are non-existent. Now in this case, in this particular presentation, we relax that assumption. Now we have cash flows happening in between, and these are constant cash flows for simplicity. Later on, we can actually relax that assumption and make them variable cash flows. It's pretty straightforward in Excel. So what we'll do is compute the present and future values of annuity and annuity due. The definition of annuity, therefore, would be that these intermediate cash flows that are happening are constant. And annuity due we will define in just a little bit after that. We'll compute the present value of perpetuity. And then after this presentation, in the subsequent presentation, we'll distinguish between different loan types and compute the interest and the nature of repayments on those loans. Finally, we'll relax the assumption. So far what's happening is our compounding period is the same as the number of same as each intermediate period. But what if compounding happens in between the number of years? So we'll have to find out an equivalent annual rate and an annual percentage rate. So we'll compare and contrast those and find out how they make life even more interesting with compound interest. So now let's talk about investment and future value of multiple payments. So let's assume that we want to save some constant amount for the future, and therefore we are interested in finding out the future value of this constant amount, assuming it's growing at a certain rate. And since these intermediate payments are a constant dollar value, we call this kind of a cash flow as annuity. So the intuition now here is, for simplicity, let's just say we are saving for 4 years, $250 each year, and therefore equally spaced, and the annual rate is 10%. Notice how we said 4 years, rate for year is 10%. Well, that's going to get disengaged in two presentations, or one presentation from now. And these are the same variables in the time value of money equation. So, looking at it on a number line, let's assume that at t equals 0, we're here. We start saving money starting t equals 1. At the end of our first year, we put in $250 for investment. In the second year, we put $250. In the third year, we put $250. In the fourth year, we put $250 and immediately withdraw everything. So the fourth $250 does not get a chance to grow. Does that make sense? Right? So the future value of that $250 is $250. Right after we insert the $250, we take everything out. Now the way we treat these cash flows are, we respect each individual cash flows contribution separately and then add them up all together. So the fourth $250 is worth $250 because it doesn't get a chance to grow. But the third value of $250 gets a chance to grow, but by only 1 year. So it grows by 1 year, and since the rate is 10%, as mentioned here, it grows by a compounding factor of 1.1 to the power of 1. The power of 1 comes because it only has 1 year to grow. So the amount, the starting value is $250, and it grows by 1 year at 10% to become $275. Similarly, the investment we made in the end of second year, this one, $250, will have 2 years to grow. So it grows in 2 years at the value of 1.1 to the power 2. So initial starting amount is 250, that is this, times 1 year 1.1, the next year 1.1, so 1.1 to the power of 2, or squared. which makes it 302.5. Now, the money that we invested at the end of the first year has the maximum time to grow. So it grows by 1 year at 1.1 times, second year at 1.1 times, and third year at 1.1 times. In other words, it grows through 3 periods at 1.1 to the power of 3. So the 250 times 1.1 to the power of 3, which makes it 332.75. If we were to calculate the contribution of each of these at time t equals 4, then we need to add these values at that point of time, because it's meaningless to compare this 250 with this 250. Since it was invested earlier, it is much more powerful than that 250. So the total value is now 1160.5. Now this can be easily calculated in Excel using what's called as the future value of multiple payments in an annuity in the time value of money equation. So how do we do that? In that case, our number of periods is 4, rate of interest or discount rate is 10%. Or remember, any percentage can be expressed as decimals and vice versa. Just multiplying it by 100 gives a decimal, converts a decimal to a percentage. Dividing it by 100 will make the percentage into a decimal. So 10% divided by 100 is 0.1. Next, PV is 0. Since we did not start with anything, all we're doing is we're just investing at equal points of time in between 1, 2, 3, and 4 years from the number line. Since we are investing this money, the payment will be negative. Remember, again, it's just a consideration. It's just a relative consideration because we want the final answer to be positive. We will use the PMTs to be negative to balance it out. That's the important thing here to remember. And the answer we get, well, is the same, 1160.25. So let's see that in Excel. Again, we're working on this sheet here. So we're going to lay this out, T and cash flow. At T equals 0, there's no cash flow. And then we just create a 1, control D2, control D3, control D4, 250. Now, when we lay out these cash flows, there is no need to put a negative sign because this is just our formula. Now, in order to make it grow to a future value, so calculate the future value of this 0. Well, this 0 today will grow at 1 plus, oh, we forgot to insert the rate. We'll insert that rate, but we'll have fixed the cell. So 1 plus $1 to the power. Now, how many periods will this grow? Well, it'll grow by 4 minus 0 periods. So $7 minus $3. So this will grow by 4. This will grow through 4 periods. This will grow through 3 periods. So 1 plus, oh, since we have not inserted a rate, I believe the rate was 10%. So now we've inserted the rate. So look, E4 is the cash flow times 1 plus $1, this one, the red color is associated with the red box. So 1 plus rate to the power, it's going to grow by 3 years. So not $3, but just we have to go back up and make it D3. So this is D3. So this becomes D4. So this cell changes, but the $7 keeps the 4 fixed. Why do we want that fixed? Because now we want this to be 3 periods, then this to be 2 periods, and this to be only 1 period. So this upper cell will keep changing, but the lower cell will remain fixed. And the lower cell is actually D7. And since we want to fix the D7, we put a $sign on the top of the 7. All right, so this $250 grew for 3 periods. This particular $250 grew for only 2 periods, or difference of 4 and 2, or D7 minus D5. Then the next $250 grew for only 1 period, which is D7 minus D6. And finally, the last $250, poor $250, it didn't grow by anything, D7 minus D7. And then when we add all of these together, what we get is the same value. Oh no, sorry about that. There we go, 1160.25. Now, This kind of a laid out elaborate cash flow analysis was just for illustration. You could do that, but you could also do something like this: equals FV, the rate is 10%, the number of periods is 4, the payment value is minus 250, the present value, what do we insert today, is nothing, 0, and the type is end of the period consideration. We're going to relax that assumption in this presentation. Is 0. So it's end of the period. And the answer is same, 1160.25. Going back to the PowerPoint. So now we got the same answer for the annuity. The key points are, this annuity is called 4-period annuity. Why is it called 4-period annuity? Because it's got 4 cash flows. Now note that the cash flows do not start, the annuity starts at 0. So I'm going to make it green color. Annuity starts at 0, but the cash flow does not start at 0. The cash flow starts at 1. Since it's a 4-period annuity, it has 4 cash flows. So 4 cash flows each, cash flow of $250. Moving on. Bring all the cash flows to the same point in time by using compounding. So where are we bringing them? We're bringing them to t equals 4. Now we could have brought them to t equals 7, 8, etc. by using an appropriate way. This is not the, so we have to learn that in this class. Now add the equivalent value of each cash flow together. So we added the equivalent value. So remember, this 332 has now gone to period 4. This 302 has gone to period 4. This 275 has been found by compounding the 250 to period 4, and the 250 is already available at period 4. So the sum total is 1160.25, or the sum of the equivalent values available for each cash flow at time t equals 4. And then this can be easily extended to multiple unequal cash flows. All we got to do is, now for unequal cash flows, this function will no longer be valid. Why? Because the single value of 250 is only going to work for the function. But if there are multiple values, which is why the elaborate cash flow diagram was shown in this presentation. So for example, if it's 112 and then 375 and then 275 and 200, look at how easily it has calculated the value. So all we need to do is insert them in the cash flow diagram, lay them out, find out the compound value, and by the way, this can also be found out by using future value function. FV rate, fix that. So $1, comma, number of periods is going to be the difference. So difference of $7 minus this particular value. The payment now will be 0 because this is a starting value. Each cash flow is a starting value. So minus 250 and then 0. Same thing. Control D. And so you can see the FV function will also give us this future value, just like the formula is giving us. They're the same thing, right? So, and then sum them up to get the same answer as well. So it's pretty straightforward to use multiple ways to get the same answer in Excel. Now, let us connect these present and future values together. Would there be a present equivalent of these future values? Of course there is. So let's first of all understand it. The first method is understanding it through the cash flow diagram. So at t equals 0, as you remember, there was nothing available. At t equals 0, we invested 250. At t equals 2, we invested 250 more. At t equals 3, we invested another 250 as we did at t equals 4. Now, instead of finding out the value at the end, the question we asked is really, can we start with one lump sum amount today that will make me indifferent between these 4 investments and a single investment? What would that single investment be? That's the question being asked. So now we have to discount each cash flow. The first cash flow that we discount is the 250, taking it back by 1 period. That gives us 227.27. So this is called discounting, and 1 divided by 110, 1.1 to the power 1 is called the discount factor. Similarly, 1.1 to the power 2 in the denominator is called the discount factor for the second period, and so on. So when we want to bring back the $250 available to us at the end of second year to today, we divide it by 1.1 to the power 2 to get 206.61. The third cash flow of $250, if we pull it back by 3 years, then we divide it by 1.1 to the power 3 to get 187.33. Finally, the fourth cash flow, if we need to discount it by 4 periods, again see 1, 2, 3, 4 periods. So we divide it by 1.1 to the power 4 to get 170.75. So the power of the first cash flow is very little. We have to start with a big amount to get 250 after 1 year. We have to start with a slightly smaller amount to get 250 at the end of the second year. We get to start with even lower amount to end up with 250 at the end of the third year. And we get to start with the lowest amount to end up with 250 at the end of the fourth year. That's why the present value for the fourth cash flow is the smallest. That is the killer effect of time. The sum total of that is 792.47. Now, this is just an illustration. That's why the entire cash flow diagram was laid out. In real life, we don't do this. All we do is take it to Excel and use a TVM equation. NPER is 4, rate is 0.1, or if you want to use a percentage, then 0.1 times 100 or 10%. And then future value, remember, we are finding out the equivalent present value. So the future value, we're not getting any cash flow at the end. So the future value is treated as a cash flow. Nothing is available. The $250 are all accounted for in the PMTs. There are 4 payments. If on top of that we were to get something else, then that something else would become a future value. And we can illustrate that very easily. So the PMTs are the payments, the intermediate payments are all given a negative consideration because we want the return positive, present value to be positive. That's all. So the answer is 792.47. How do we do that? Well, there are multiple ways to do that. So we're going to keep utilizing this table here. So let's go to present. To avoid confusion, let's just replicate the rate here and hide the cells. So we just keep the cash flows here, hidden the cells. Now let's find out the present value. We can do this by using 2 ways. I'm going to use the straightforward formula way, and then it can be easily, there are multiple ways of doing this. So first thing is the present value of $0 available today is $0. So to bring it back to present, we had to divide it by 1 plus $1 to the power of 0. Then E4 divided by $1 to the power of 1. D4, the cell D4 is purple and this is purple. Let's see, is it purple? Let's see if I can make it zoom in and make it bigger. Oh, because I'm in the formula. All right, so zoomed in. And then let's see, this is purple or violet. I'm sorry, palette colors. So this is the same color as this. That's D4. Keep going. So now we discount the 250 divided by 1.1 to the power of 2. 250 divided by 1.1 to the power of 3. 250 divided by 1.1 to the power of 4. And then shift control 1 will make them 2 decimal places. Add them up equals SUM. Of all the cash flows, 792.47, which is exactly what we got. But wait a minute. There are multiple, Alt OCU, unhide the cells. There are multiple ways to get it. Remember this, what is the 792.47? It's an equivalent value today that if I invested it for 4 years, I would get 1160.25. Now, you might say you don't believe me, right? Let's show it. So which should we use? Should we use the compounding formula or the future value function? Let's use both. Equals up arrow times parenthesis 1 plus $1 to the power of 4 will magically give us 1160.25. Still don't believe it? No problem. Equals future value of I1, that is a rate. Number of periods is D7, comma, the intermediate payments. Now look, we are only finding out the equivalent value of a single value now, right? The present value is 792 for all the 4 cash flows. So once we found out an equivalent value, we don't need to deal with the 4 cash flows. So the single value is going to be the present value. So intermediate payments are disregarded. The present value is minus I8 and the type is 0. Magically, believe it or not, the answer is going to be 1160.25. Here we go. Ta-da! Okay, can we do it the other way around then? Well, we had this 1160.25 all along, so we could have done the 792 from the 1162. Sure, equals this divided by, discount it, 1 plus I1 to the power of 4, which is D7. 792,147. Okay, one more way, equals PV of I1. Just discount the future value. Number of periods is D7, comma, no payments, remember it's an equivalent value now, minus F10, comma, 0. What are we going to get? We're going to get 792.47. So there are multiple ways of getting the same answers. Just need to get the cash flow straightened out. What is the real equivalence we're trying to find, and then everything will be clear. So that's a 792.47. Moving on. Now, what is an annuity due? It's pretty interesting, and it has got a practical application, as we're going to see in a little mini case here in this particular presentation. Annuity due, annuity's cash flow starts at t equals 1. Annuity due cash flow starts at t equals 0. Remember the type in the TVM equation? The type is 0 usually so far. Well, for annuity due, the type becomes 1, because now the cash flow starts at t equals 0 and the annuity due also starts at t equals 0. Let's see this. Here, the annuity started at t equals 0, but the cash flow of an annuity starts at t equals 1. Some examples are like investments, loans, etc. Some examples of annuity dues are when we want the payment to be made immediately, like house rent, like insurance premium payments, etc. So these are annuity dues. So it's more valuable than annuity by a factor of 1 plus R. Why? Because see, if the 250 instead of being available at 1 year later is available now, it becomes more important to us by that factor of 1 plus R. Why? 1 plus R is the compounding factor, right? Or the discounting factor. And therefore the entire annuity due is more precious than the annuity by that factor, because it's available more recently than annuity. So let's look at our example again. Now in this example we have 4 cash flows of 250, but instead of being available at t equals 1, the first $250 is now available right away, and the fourth $250 is available at the end of the period 3. So to see that, let's just hide all this now. Let's just create a new set of cash flows right here. So this is time, this is the payment, value of payment, and then we'll find out, what do we need to find out? Present value? Sure, it looks like we are finding out the present value. So present value of each payment. All right, and so the time is 0 equals this plus 1 plus 1 plus 1. And that's it, we're done. So $250 here, $250 here, $250 here, and that's it. This is a 4-period annuity. Look, the count, the count is 4. 4-period annuity, but the third cash flow is at the end of the period 3 itself. Like you prepaid for the 4th period at the beginning of it. So at the end of the 3rd period, you prepaid the 4th period. That's why it's annuity due. Now, what's the present value of 250 right now? Well, if the rate were still 10%, so I'm going to write that down. Rate is 10%, and just make a nice table out of it. OEB Alt OI. Takes a second to pop up. Enter. Okay, so equals this divided by parenthesis 1 plus $12, that is this cell in the red, to the power of D14. The purple colored cell. And now all we got to do is drag it down. E14 will become E15, D14 will become D15, but the rate will be where it is. That is 10%. Correct? And correct? The red cell has become constant. I mean, it's pointing to the same value because the rate is the same across all the periods. So this is the present value for all these cash flows. So equals sum of all of them. Now, could we have used another method to find it? Yes. We could have used the PV function equals PV of each cash flow, right? So PV rate is F$12, F$12. The number of period is this cell here, comma, the payment is 0 now because these values are each treated differently as a future value, minus the future value, and the type is 0. So 250, 227.27, 206.61, same, exact same things. Now, this is the present value of the annuity due. Can we find out the future value at the end of 4 periods? Yes. At the end of 7 periods? Yes. Because now we have equivalence. The equivalent value today is 871.71. In other words, if I was an investor receiving, paying $250 at the end of period 0, 1, 2, and 3, the equivalent sum that would make me indifferent between waiting for 4 years and getting something right now, that would be $871.71, which is exactly what we got here. But notice how the time periods, instead of the cash flows being available at the end of it, were available at the beginning of it. Now, can we use annuity due using the TVM, time value of money equation? Yes. Equals present value. The rate is F dollar, oh, well, put dollar because I'm not copy pasting it anymore. F12, the blue cell. Number of periods is 4. There are 4 payments. That's why it's 4. The value of each payment is minus E14 or $250. Look at the red cell. And the future value, meaning what are we getting in the end? Nothing special. So 0, because that's it. Just the 4 cash flows, right? And the type, instead of being 0, will be 1. If we make that mistake, otherwise it's just going to treat it as annuity, not annuity due, if we put it as 0. So this is an annuity, but this makes it annuity due, giving us a value of 871.71. Now, what is the connection between these 4 cash flows of $250 and the annuity cash flows of $250? 1 plus R. So what we need to do is discount this by 1.1 to get 792.47. How easy was that? Why? Well, we said that each cash flow is more precious by the factor of 1 plus R. And that's what's going on in an annuity due. Okay, so moving on. Let's extend an annuity to forever. Now this is a very interesting example, and for the sake of time, not going to discuss that in Excel, but very interesting example. Perpetuity has infinite cash flows, but think about it. What is the present value of a cash flow 100 years later? So if I receive $250 after t equals 100 years, then the present value of that at 10%, 250 divided by 1.1 to the power of 100 is virtually 1 cent, 2 cents. It's meaningless. In other words, if this time period becomes more and more farther, the present value is close to 0. The farthest cash flows are meaningless to us today. So perpetuity that has actually got infinite cash flows, its present value of these faraway cash flows have no significance to us today. And so therefore we can show that an annuity converges to a value if time t goes to an infinite number. So what is a perpetuity? Infinite cash flows. But actually what happens is it becomes equivalent to an annuity that is large enough. So the present value of a perpetuity is each cash flow divided by the rate of discount, R. That's it. So C is the cash flow. In our case, it was 250, right? So if this was to become a perpetuity, all we need to do to find out the present value is 250 divided by 0.1, not 1.1. It's perpetuity, or 2,500. So in the long run, the present value of all the cash flows of that annuity, if they were to keep going forever, would converge at $2,500. That's all the implication is. Now, if you really want to see it, I can take a quick minute to show you. So 1 equals 1 plus, equals 1 plus 1. And then let's take it to Alt V Z 0. Let's take it to Control C, Control G, A 500 first. Just let's take it to 500 periods, okay? And let's put $250 equals this, and then black cross, double click. So we entered all the values, find out the present value divided by 1.1 to the power. It's very straightforward. And then black cross, double click. And what I'm going to do now is just add these present values up together, equals C1 colon C 20,000. So when we have already with 500 values, we have seen convergence, whether it's 500 or 480. So look, the present value of all these cash flows is 2,500, right? So if I remove the last 20 cash flows, what's the present value? So in other words, let's assume that I don't receive the final 20 cash flows. It's still 2,500. What if I remove another 10 cash flows? Or I don't know, I mean 30 cash flows? Seriously, they have no meaning, no effect on today's present value. But if I remove today's cash flow, the present value drops. Look at the power of cash flows today versus cash flows in the future. That's a perpetuity. So essentially this 2,500 is nothing but 250 divided by 0.1. It's basically the present value of infinite cash flows, but not really infinite, large enough cash flows. Okay, now let's go on to more interesting application of compound interest and multiple cash flows. This is a mini case, and it's a really fun case, at least I think. So Grace F just graduated from college. She is interested in creating a nest egg. What is a nest egg? Retirement funds. And so she's thinking ahead of time. She has got a long life ahead of her and wants to save everything and become a multimillionaire by the end of her retirement. So let's assume that she invests annuity, constant payments, $12,000 per year, which is also the compounding period, for 45 years. She's really bullish about it and wants to make a great living at the end of her retirement. So 45 years, but she doesn't know what to do. So she goes to her financial advisor, who tells her, the financial advisor, Mr. Matt B, suggests to her that 11% is the going rate of return on stock markets. What he says is, don't ignore the little fluctuations that take it down or fluctuations that take it up. On an average, the stock market has increased every year by 11% historically. And looking at the current conditions, because the markets have come down slightly, we can invest for 11% returns for 45 years. That's the advice of Matt B to Grace F. Now, so Grace F is really confused. What should be the value of these $12,000 invested per year after 45 years? Now we could do the elaborate cash flow diagram. If you want to do it, it's already here in the table. Just right click, open worksheet object and enjoy. But the simple way is using the PFV function, right? So let's go back to this sheet and just write down the numbers. So it's $12,000, $12,000, 45 years, rate is 11% per year. And all we do is equals future value at the rate of this 11%. Number of periods is 45 periods. The constant payment we make is $12,000. That Grace makes is $10,000. The value today, nothing. She will start after the end of first year, and the type is 0. And so it's all pound signs because it's a large number. She actually ends up with $11 million at the end of 45 years with the compound interest. Well, if you just see the nominal value of this, if she kept it under her mattress, would be nothing. It's just $540,000. But the power of compound interest actually makes it $11 million. So that's what we got, $11.839 million. So that's the value that Grace F has. But wait, she's interested now in disinvesting it. So she goes back. She's now accumulated her wealth after 45 years and now approaches Matt B again. I'm a multimillionaire. What can I do with my money? I want to disinvest it. assuming that I will disinvest for 25 more years, based on my suggestion of my friends, the rate's still 11%, says Matt B. And so now, here in this case, Grace F wants to start withdrawing immediately. Get it? It's not annuity anymore. It's annuity due, right? So she wants to start withdrawing immediately for 25 years. What would be that constant payment? So now what we do is take this as a starting value. So find out the payments that correspond to this present value. Payment at the rate of 11%. Number of periods is not 45 but 25. The present value is minus 11,000. Remember, we want the payments to be positive. That's why the present value will be negative. So it's just a loan consideration. At the end of all this, the future value will be 0 and the type is 0. Press enter. She can withdraw $1.4 million per year and still be happy. And if you want to see the details, they are in this table right here. How the cash flows actually decrease the running present value to 0. But see how simple it is. The time value of money equation gives us a single number that actually puts everything clear. Okay, so we can withdraw $1.26 million per year. Nice. For 25 years. And so to conclude, annuity has equal cash flows available at the end of the period. Annuity due has them at the beginning of the period. But bottom line is this: to find out the equivalence, we must bring all the cash flows either by compounding or discounting to the same point of time to compare them. So the present value is the equivalent value today. The future value is the equivalent value at a different point of time in the future. But again, that point of time is same for all the cash flows. Annuities and annuities due have many applications. We just saw a couple of them in this video. In next presentations, we'll talk about different loan types, annual percentage rate, equivalent annual rate, periodic compounding, and basically lots of interesting applications of finance. And that's Chapter 5, Part 2. Thank you for listening.